So yesterday, we did the first couple questions on our homework that has graphs of force versus time and force versus distance. So let's finish the rest of it here. Um, so if we look at a F versus T graph, before we ever even get to questions, we know that the area under the curve is equal to the impulse, which is equal to the change in momentum. So that's our mentality as we go into questions. So what's the change in momentum? Change in momentum, we know we got to find the area under the curve. First 3 seconds here, we've got ourselves a triangle. 1/2 base times height is 1/2 times 6 times 3, or 9 kilogram meters per second as our change in momentum. What's the change in momentum of the object during the first 5 seconds? Well, we know that this is a change in momentum of +9. As soon as we dip down here below the axes, we've got a negative force, which would cause a negative change in momentum. So what's the area in this region right here? So, that area is going to be equal to, base times height. So our area, let's go area for time 3 through 5 is equal to base times height. Well, that's 2 seconds times um, uh, 2 seconds times a height of -4 newtons. So that area is -8 newton seconds, or kilogram meters per second. So if we have a +9 and then a -8, my overall delta momentum then is 1 kilogram meter per second. How fast is the object moving? Well, that object is going to be moving. Delta P is m delta v. So therefore, well, we don't want to put that as an equal sign. Delta P divided by m is going to give us our delta V. So delta P is 1 kilogram meter per second, and we've got a mass of 2 kilograms. So delta P is going to be 0.5 meters per second. Now, since the positive change in momentum is bigger than the negative change in momentum, this is going to be a positive velocity and overall positive change in momentum. Again, before we look at any question, we notice we have a force versus time graph. So again, area under the curve is impulse, which is change in momentum. Question 6 I like a lot. If the football player is initially at rest, at approximately what time does the football player return to rest? Well, if the football player is initially at rest, and then there's a force placed on the football player, then that football player is going to accelerate it and change his or her speed. So therefore, when we go above here, we have a positive change in momentum, which means the football player is going to gain speed whenever that force number is above the x-axis. And then there's going to be a negative change in momentum down here. So basically, when's the thing going to return to zero? Well, if it gains, let's say 10 kilogram meters per second of momentum, it doesn't go back to rest until its overall momentum is going to be zero. So anything this thing gains up here in positive momentum, we've got to get an equal area someplace down in here. The question is, where does that occur? All right, so our area under the curve in the first part of this thing, right here, so our positive delta P is equal to, 1/2 base times height. So that's 1/2 a base of 0.2 seconds times a height of 400 newtons. That's going to give us a positive change in momentum of 40 newton seconds. Now, where is this thing going to be an equal amount in the negative change in momentum? Well, look at if we go another 0.2 seconds, and we come down here, well, we know that the change in momentum wouldn't be as great because at 0.2 seconds, the force had gotten up to 400 newtons. Well, here, it's only going to get itself up to, 250 newtons. Yet, when does this thing get to 400 newtons? Well, it gets to 400 newtons at 0.5 seconds. But 400 newtons and zero point 0.3 seconds is going to give us a bigger negative delta P. So then therefore, we know that this thing is going to reach a negative change in momentum of negative 40 someplace between that 0.4 seconds and 0.5 seconds. In this question, that's all it's looking for is approximately, right? We could do the math out, but like, can we reason our way through that is even better. What's the approximate change in momentum of the football player during the first 8 seconds? Well, now, we've already got our delta P up here between the first 0.2 seconds. Well, what's our negative delta P for 0.2 seconds to 0.8 seconds? As again, it's a triangle, 1/2 base times height, so that's 1/2 times 0.6 seconds. And then, what's that force down here? That's negative 800 newtons. So our change in momentum, half of 0.6 is 0.3 times 800 would give us minus 240 newton seconds. Well, if I had a positive 40, now I got a negative 240, therefore my delta P from 0 to 0.8 is going to be negative 200 newton seconds. How fast is the football player going to be going? Well, momentum equals m times v, so P divided by m is equal to v. So the new momentum at that time frame is negative 200 newton seconds divided by a football player's mass of 100 kilograms gives us a velocity of minus 2 meters per second. Now, how fast is the person going? Well, they're going 2 meters per second. The minus there just dictates a direction for us. Now I go to this graph down here. It's a force versus position graph. So again, before we even look at the questions, we're saying to ourselves, area under the curve is equal to the work done, which is equal to the change in energy. What's the net work done on the object as it moves to the 4-meter mark? Well, again, here I've got a positive work right there, and then I've got negative work, down in here. So our positive work, so the work done from 0 to 2 meters, is base times height, or force times distance, which is 40 times 20, or 80 joules. Our work done from 2 to 4, it's also a rectangle, base times height. It's also 2 seconds, but it's negative 20. So 2 times negative 20 gives us negative 40 joules of work. What's the net work done? Therefore, positive 40 joules of work. Where does that positive 40 joules of work go? It goes, in this case, to change the kinetic energy, which is 1/2 mv squared. So twice the work divided by mass square rooted is equal to v. So 2 times 40 gives us 80. 80 divided by 10 gives us 8. The square root of 8 is about 2.82 meters per second.